We're going to be looking at additional properties of binomial distribution, section 5.3, and we're going to remember that histograms have discrete numbers on the bottom and then probability up the vertical axis. And so when we're looking at those histograms, there are a couple characteristics for one of the binomial distribution. And so in your notes, you're going to see that as you draw a histogram, these numbers down here are going to be 1 unit wide. So it's usually starting at -1/2 to a +1/2, and then you'd have 0 as your first counting number, like 0 out of a certain number of successes. And then the probabilities would be over here. And so the closer P is to 1, the closer P is to 1 or the closer P is to 0 will tell you the skewness of the histogram. So this is in your notes on 1F, and you're going to see that this should hopefully make sense. If you had a histogram that looked like something like this, where it's skewed to the right, when you're looking at all of these numbers, and the higher the probability to the right means that, for example, if you had 7 trials, the ones that are successful, the highest successful rate occurring ones, are the ones that are closest to 7 trials. In fact, 7 out of 7 trials that are successful has the highest probability, and then 6 out of 7 would have the next highest probability. That means that the probability of success is very high, which means that the tail would be skewed, would go to the left, which means it's skewed to the left. So the closer the probability is to 1, the more skewed it is to the left. The closer the probability is to 0 means it's going to be skewed to the right. And also you can see that the area under the curve, if this is 1, the length of 1, and this is the probability over here, you're going to see that this area right here is going to represent the probability, because 1 times the probability gives you the area. And you also know that the area of all these added up is going to equal 1. All right. There are 2 formulas that you need to know, and this is in number 2 section. They're in bold. One is where you find the mean of the binomial distribution, and to find the mean or the mu, you just take your n, your number of trials times the probability, and that's it. It's often considered the balancing point of the histogram. It would be where it balanced, if you think about it in terms of the area. And also, you would know the standard deviation is just the square root of n times p times q. That's pretty easy to find as well. Again, standard deviation refers to how spread out the numbers are, how spread out these successes are going to be from the mean. I want to just do one example, and then you'll see that this isn't too bad of a section. The example is where the student is going to try field goals and is considering that they're 50% chance of making them from anywhere in the paint, out of the paint. And so if Jim tries 6 shots, the question is, what's the histogram look like? And then what's the mean? How many attempts would you expect him to get? And what would be the standard deviation? Now, if it's 50%, you would expect him to make 3 out of 6. If it was a higher one, you'd expect them to make more than that. But there is an expected value. If you fill out your N, S, F, P, and Q, your N would be number of times, would be 6 shots. Success is the shots made. Failure is missed. And then your probability of success, P, is 0.5. Failure is 0.5 as well. And so when you make a histogram of this, it's often easiest to do something like this on a table if you can, because you have all of the probabilities for you in the table. You don't have to go back and forth with the calculator. What you're doing on this side is the binomial PDF, and this is going to be 6 shots. 0.5 is going to be the P, and then your R is going to be how many you're going to make down here, and this is going to be shots made. So the way that you can set this up is where you can actually start with 0, so it's going to go from -1/2 to +1/2, and that would be 0, and so you'd have a bar in here, and then each of these bars would have a number midpoint, so you're going to see that that pattern is going to look something like this. And again, that's the number of successes out of 6 that you're finding out. And then you're going to have a probability, and the probability that you're going to have, and what I would do when you do this histogram is just do it all at once, and you're going to see that when you go to 6 and you look up 50%, you're going to see that 0 out of 6 is going to give you a probability which is 0.016, and that means that this is the top of that bar, and if you go down, because it's symmetrical, you're going to expect 6 out of 6 to be the same probability. Again, 50%, this is going to be as likely as this. Secondly, if you make 1 or 5 shots, again, because it's 50%, it's symmetrical, and so that's going to be a different one, 0.094 or 9.4%. That's going to be like this. Now, I don't really, it's not going to bother me too much if these aren't equally spaced as you do the numbers. If you show me the exact numbers, then that's what that reflects. Then you're going to have 0.234 for making 3. Sorry, for making 2. I'm off by 1 here. That's 1. This is 2. And this is 4. Okay, so we have the same probability for 0 and 6, the same probability for 1 and 5, and the same probability for 2 and 4. And then 3 would be 0.312. And so you're looking at something like this. Now, if you did that correctly, it's a little bit tricky up here, but if you did that correctly, now it just becomes easy because you can just fill in the bars as you needed to. So we're just going to draw the bars down here. And then it looks something like that. And so the probability of getting 3, exactly 3 out of 6 would be 0.312. So the other question that you can ask is, what is the expected value of this whole experiment? What can you expect to make when you take 6 shots? And so the n times the probability would give you that. So if you're looking at your mu, n times p, you're going to have 6 times 0.5, or your mu is going to equal 3. 3 shots would be what you can expect. What is the probability? What's the standard deviation? The standard deviation is going to be the square root of n times p times q. This is going to be 0.5 times 0.5 times your n, which is also going to be 6. And when you multiply 6 times 0.5 times 0.5, you are going to get a standard deviation of 1.22, which again is indicating how spread out the number of shots would be from the mean, which would be 3. Okay, going back to here, remember what 3 means. 3 means the probability of getting 3 out of 6 in any order. The next question that I have is something that's a little bit harder, and let's say, for example, the question is, what is the probability? No. Let's say that the probability is 95%. So I'm going to say that the probability of the event occurring is 95%. And let's say in this particular example that you want to know how many shots it will take for Jim to take in order to be 95% sure that he makes, let's say, 12 baskets. So 12 shots, meaning if you know he has to make 12 shots, your n value or your number of trials is what you're trying to find here. If we're 95% sure that he wants to make 12 shots, then the question is, how many times does he have to attempt it? All right, now you could, and again, our P, I guess our P should be just a little bit different this time than 0.5. Let's say it's 0.6. Let's say he's excellent. So in this one, at least, what did I say, at least? At least 90, yeah. In order to be 95% sure, he wants to get at least 12 shots in. So at least 12. So that could mean 12, 13, 14, 15, 16, any of those. But we want to know at least 12. So what I really want to do here is to set this up on your calculator. It would be 1 minus, and then it would be binomial CDF of n. I don't know my n. This is different. I don't know how many shots he has to take. But I do know my probability, and I do know that he wants to make 12 shots. So now we have something like this where I have to find my n. Now, that's a variable in your calculator, which is a problem. Also, I know that this has got to be, let's say, greater than or equal to 0.95. Well, how do I do this on the calculator? The way I do this on the calculator is going to be trial and error, because there isn't a way that it can just solve for that. So, for example, I'm going to go 1. Yeah, I made a mistake here. The mistake should be, this is 11 No, yeah, that should be 11 because we said that he has to make at least 12, which means I'm subtracting off 0 to 11, right? 0, 1, 2, 3, all the way to 11. 12 is what we want. So it's like, these are my two groups. I want to subtract off 0 through 11. So that's that cumulative 0 to 11, which is right here. Back to this. 1 minus binomial cumulative number of trials. Let's say it's going to be 30 as a guess. 0.6 is what I want. I want to subtract off the 11 to make it 12 or more. And then when I go ahead and do this, just as a guess, I'm at 0.99% or 99%, which means I'm high in terms of the minimal amount of shots that you need. So I have to reduce this 30. Again, remember, you guys trying to remember what you're trying to find. You're trying to find your n. I want to reduce that until I get closest to 95 as possible. So let's try 21. That's way off. So it's between 30 and 29, 30 and 21. So let's go to 28. Now I'm closer. With very few number of attempts, you can get pretty close. And so that's not there yet. Even though it rounds up, you're still below. So that tells me that 27 is going to give me my answer. 27 attempts is going to be the first time that he has 95% certainty that he's going to clear 12 shots or more. So that's going to be your n is going to equal 27 shots. When you get to those problems, think about trial and error. It's the easiest way to do it. And tomorrow we're going to get into the last part of this section, which is geometric distributions. And then there'll be a test on Friday.